Hello, good morning students. In this topic, we are going to discuss about equilibrium of rigid body. We already know what is meant by rigid body, the body which is having a fixed shape. The distance between the particles will not move or will not change when the body is moving, that is called rigid body. So, here we are dealing with equilibrium of rigid body. When can we say the rigid body is in equilibrium? A force changes the translational state of the motion of a rigid body. That is, it changes the total linear momentum. If I apply a force, obviously you know there will be a change. Force can cause the change in the state of the body. So, there will be a change in the linear momentum when the body moves. Now, a torque changes the rotational state of motion of the rigid body. That is, it changes the total angular momentum of the body. So, here I am mentioning the two aspects. What is the first aspect? A force which changes the translational state, that will change its total linear momentum. So, when I am applying a force, there is a change in linear momentum. See the second sentence, when I am applying a torque, there will be a change in the angular momentum. So, angular momentum will change only if there is an external torque. Linear momentum will change if there is an external force. Now, see this, a rigid body is said to be in mechanical equilibrium if both its linear momentum and angular momentum are not changing with time. So, the rigid body is in mechanical equilibrium if there is no change in the linear momentum and there should not be any change in the angular momentum also, which means total force should be 0. No change in linear momentum. You see the first equation, first statement. Force will cause change in the linear momentum. So, if total force should be 0, the body is in translational equilibrium. There is no change in the linear momentum. Similarly, if the total torque is 0, the body is in rotational equilibrium. There is no change in the angular momentum. So, these are the two states of equilibrium, translational equilibrium and rotational equilibrium. For translational equilibrium, the net force will be 0, and for rotational equilibrium, the net torque is 0. Okay. So, you can see a figure here. The body, this is a rigid body. This black thing is a rigid body, and this is the axis where the body is fixed. So, body can rotate about the axis or body can move up and down. It can wobble. So, just see, I am applying a force downwards here. I am applying a force downwards here. These two forces are equal and opposite. Sorry, these two forces are equal and in the same direction. So, what is the net force? Net force is 2F. What is the net torque? Net torque is 0. Net torque is 0 because one force, you see my blue arrows, one force will cause the body to rotate in the clockwise direction. This force is causing the body to rotate in the anti-clockwise direction. I will say once more, this force helps the body to rotate in the clockwise direction, and this force helps the body to rotate in the anti-clockwise direction. So, the clockwise torque and the anti-clockwise torque are equal because F is same and the perpendicular distance is L by 2 in both the case. So, clockwise torque is equal to anti-clockwise torque so the net torque is 0. That is why the body is in rotational equilibrium. So please draw the figure and note down that. Now see the second figure. Here what I am saying, this is the rod, again the same rod, but now I changed the direction of force. One force is acting upward, other force is acting downward. So the net force is 0 because F minus F. Net force is 0. But think about the net torque. See here, this force is causing an anti-clockwise torque. This force is also causing anti-clockwise torque. So here also anti-clockwise torque, here also anti-clockwise torque. So torque is getting added up. So torque here is force into perpendicular distance, that means F into L by 2. I will write here. Torque is equal to F into L by 2, that is the first case. This is the force, this is the perpendicular distance. F into L by 2, that is anti-clockwise. Here also it is anti-clockwise. Again the distance is L by 2 only. L by 2, the distance from the force to the axis of rotation. So I will write plus F into L by 2. So F into L by 2 plus F into L by 2. What is it? 2F into L by 2, which is F into L. That is why I wrote net torque is F into L. So this is translational equilibrium. Okay. Yes, please draw the figure and note down that. And here you can write one more thing. The net torque will be F into L by 2 minus F into L by 2, because one is clockwise, other is anti-clockwise. That is why the net torque is 0 here. That also you just please make a note of that. Okay. Now the next thing, couple. You are familiar with the word couple. What is meant by couple? Two things together. They will move together, they will walk together, they will do things together. That is what is called couple. So here in physics, when we say about coupled force, I am talking about coupled force. So coupled force means two equal and opposite force acting on a body. Two equal and opposite force acting on a body. That is called couple. So the pair of equal and opposite forces with different line of action is known as a couple or torque. A couple produce rotation without translation. That means if I am applying a couple, the body will undergo translation, that body will undergo only rotational motion. No translational motion is taking place. Example, when you open the lid of a jar, you are applying the couple on it. For example, I will just say I am having a water bottle and I want to open the cap. See, this is the water bottle and I want to open this cap. Is it easier to rotate using one finger or to use two fingers like this and turn? See, I am applying two fingers and turning it. You can see one finger is acting a force in the backward direction. That means my point finger is acting a force, is giving a force in the backward direction. My thumb is giving a force in the forward direction. As a result, the thing will rotate. The lid is rotating. and it is opening. So it is easy to close and open the lid with 2 fingers because one force is one force is in the forward direction, other force is in the backward direction. So there will be a rotational force only rotational force is taking place, no translation is taking place. Such a force is called couple force. Okay, so it is easier to open the lid of a bottle with 2 fingers than opening with 1 finger. Another example, the handlebar of a cycle. We are holding the cycle like this, the handlebar. If you want to turn, what will you do? I suppose I want to move towards my right. So what I am doing is I will hold like this and I will give one force in the forward direction, other force with my right hand I will give a force in the backward direction. So I am turning it like this. One is going forward, other is coming backward. So I am applying couple force. The steering wheel of a car, to turn the steering wheel of a car, I am applying the couple force. One is forward, other is backward. So when I apply couple force, the mechanical advantage is more. That means I need to apply less force to provide more turning effect. See, in the bottle case, I am using 1 finger to turn. I have to apply more force, only then it will turn. But when I apply a couple force, with a very less force, it can be turned. Okay. So let us see the figure. One force is in this direction, other force is in this direction. So torque acting. Torque acting is tau is equal to force into perpendicular distance. So I am using the first force and the perpendicular distance is L by 2. So F into L by 2 plus, when I apply the second force, again the perpendicular distance is L by 2. So torque is equal to F into L by 2 into 2, that is torque is equal to F into L. That means when I am applying a coupled force, you can see torque is not force into this distance. This is the axis of rotation. So usually we take force into the distance from the axis of rotation. But here what I am getting, F into L. L means the entire distance between the 2 points where the force is applied. That means distance between these 2 points. Usually when I take the torque, I have to take the distance from the force towards the axis of rotation, this distance. But when I am taking a torque, I am getting this as the distance in the answer, which means, as I told you, mechanical advantage is more. If the mechanical advantage is more torque will be provided by the application of less force. So it is easier to turn. That is the advantage of coupled. Okay. Yes. Now listen here. An ideal lever is essentially a light rod pivoted at a point along its length. This point is called fulcrum. So here you can see in my figure, this is fulcrum and this is the load, that is the effort. You have already played this seesaw, you know. When we play seesaw, if one person is having more mass, other person is having less mass, very less mass, it is difficult. Suppose you are trying to play seesaw with a boy who is studying in first standard. Will you be able to do it? No, because your mass is greater, his mass is very much lesser. But we can do it. In the normal way we can't, but I will tell you how to do. What you have to see is the seesaw will move up and down if it is perfectly balanced. That means clockwise torque and anti-clockwise torque should be same. So what I am saying is, if you are having more mass, you sit here and keep the fulcrum closer towards you, so that this distance d1 is less. Okay, and ask that first standard boy to sit here. So this distance is more. His mass is less, but this distance is more. Now, for the rotational equilibrium, clockwise moment is equal to anti-clockwise moment. So when you are applying a force here, what is the torque acting on you? What is the torque acting here? F1 into d1. So I will write here F1 into d1. F1 into d1. Now he is also applying a force down. So what is the moment of force here? This is the moment of force in this direction, F1 into d1. When he applies force here, the moment of force will be in this direction. Moment of force means torque. Torque will be in this direction, and it will be F2 into d2. For equilibrium, what should I say? F1 into d1 is equal to F2 into d2. So I am writing like this. For equilibrium, F1 into d1 is equal to F2 into d2. So from here, what is F1 by F2? F1 by F2 is equal to d2 by d1, which means if you are having more mass, force will be more, but you just decrease the distance by moving the fulcrum closer towards you and give him more length. This arm is called lever arm or effort arm. So you give the effort arm more. So his mass is less, but his effort arm is more, so that he will get also the same torque. He can also produce the same torque. Then this is possible. This is called principle of moments. Okay, so please draw the figure and take down that. So that's what I have written here. The mechanical advantage is greater than 1. That means a small effort can be used to lift a large load. So here the child is doing the effort to lift you. So child can give a small effort to lift a large load. Understood? Because the mechanical advantage is greater than 1 in this case. Okay. Now, what is meant by center of gravity? The center of gravity of a body is that point where the total gravitational torque on the body is 0. Or we can say gravitational torque is 0 means what? Due to gravity, the body will not fall down. See, for example, this bottle, I am holding it like this. It is staying. Now, what happens if I keep the bottle like this and then leave my hand? You can see the bottle falls, because the gravity is acting here and the gravity is providing the torque. That is why the bottle is falling. Now, see, I am holding the pen like this and trying to balance it. It fell. Now, I am balancing in one particular point here. Now, the pen is not falling. The pen is steady because I am holding the pen now in the center of gravity. So, the gravity acting on this part and gravity acting on this part is same. Therefore, net gravitational torque is 0. So, it is the point, the center of gravity is the point on the body where the entire weight of the body is assumed to be concentrated. Okay, the entire weight of the body is assumed to be concentrated. That is called center of gravity. You can see here in that picture, you can see the ball is just getting balanced at its nose. So here also what we are doing is we are just identifying that point where the entire weight of the body is concentrated and the body is balanced if it is supported at the center of gravity. Now the center of gravity coincides with the center of mass in uniform gravity. If gravity is same in the region, center of mass and center of gravity will be the same point. But if the G varies from part to part, then the center of gravity and the center of mass will not be coinciding. So this will happen to only very long bodies like different planets and all. Say for example, moon is attracted by the earth. In the moon, if I take the center of mass and center of gravity, both of them will be different because it's a massive thing. So the point on the moon, the side of the moon where it is closer to the earth will experience more gravitational pull by the earth, and the other side of the moon experience less gravitational pull by the earth. So the center of gravity point and center of mass point will remain different. Otherwise, for normal bodies in the earth, for small bodies, for normal bodies in the earth, center of gravity and center of mass lies in the same point itself. Okay. Okay, that's all in this section. Thank you.